Yes.
Yeah.
Hello.
Okay. I was just searching for a meeting. So thank you everybody for coming to the Astrophysical Colloquium of Graz University. I see we have a very international list today, which is good to see, and also international or nearly domestic is our guest, Professor Dr. Eike Günther, resident scientist at Tautenburg, Thüringer Landessternwarte Tautenburg. But I joke that he's also domestic in Graz because he's a very happy guest to come to Graz, taking every excuse he can get. Eike did his diploma in Freiburg on a sun we know as a star, as a sun. Then he continued for his PhD on stellar formation, which he completed in the year 1994, and was a postdoc in London for 3 years before he became a staff member at the Thüringer Landessternwarte, where he is now this year for 25 years. And he will have his silver staff anniversary this year. And I heard they even have a ritual for that. So congratulations from my side and our side here. During those 25 years, he did several sabbaticals, 2 at the ISC on Tenerife. This is actually where I got to know Eike, with a very long discussion, a very fun discussion about today's topic. And he also spent half a year here in Graz at the IVF and the Karl Franz University. So welcome back, I think I can say. And Eike, the stage is yours.
Thank you very much, Paul, for the introduction. I hope you can all hear me. And I want to speak a little bit about the several people working on the CARMNES data. What CARMNES is, I will introduce. It's a high-resolution spectrograph to look for planets of M stars, and our postdoc Priyanka is working on that. Then Sylvia is a PhD student, but she is almost finished. And then I had 2 master students, Lara and Sarah. They were also working on the CARMNES data and looking for planets. Then say the other section in our exoplanet group is the flare section. I will also speak about flares tonight. And Priscilla and David are both working on that. Now, Priscilla I also do the teaching export, which you see in the lower left with Mambara University in Uganda. And in normal years, so not last year, I always go once a year to Uganda to lecture. And so I had a remote PhD student, Priscilla. And then, of course, we also have Arti, our director, that also works on exoplanets, Massimiliano, who looks for low-mass planets. And then Sirisha, and she developed a code to do radio velocity measurements, and Michaela and Michael, who are working on looking for planets of giant stars. And then our new subject is done by Fabienne, and she studies the atmosphere of exoplanets. So let's come to the subject. One of the main question of exoplanet research is, what is the frequency of habitable planets? And first, we have to answer the question, what is a habitable planet? And there are actually 2 definitions, and one has to be a little bit careful about it. One is it's a rocky planet in the so-called habitable zone. So what's the habitable zone? You assume that you have an exactly Earth twin, and that twin has a temperature that is so that there could be liquid water on the surface. So that's not very constraining. And then recently I read a paper and I thought this definition is much better, by Mara, and he said a planet is an object that automatically yields to life and eventually leads to evolved life. Now that is a definition which I prefer because really there's life in it, and we have to keep in mind the second part that leads to evolved life, because the prokaryotes, they consist only of 10 to the 5 molecules, whereas say big animals or so, that's 10 to the 17 molecules. So it's a vastly more complex organism. And of course, we don't want to look just for planets where there are, say, single cellular organisms, but also more evolved life forms. Okay, and the constraints for that are completely different. So in the first case, it's basically all the requirement is the distance of the planet to the star and the mass of the planet. That's it. But if you use the other definition with that you want to look for complex life forms, then of course the mass of the host star matters, the composition and the volume of its atmosphere, and the composition of the planet itself. And these 3 points are the only points I discuss in this talk. But additionally, of course, the age of the planet. If the planet is too young, maybe life hasn't evolved. The other is the structure of the system. So basically, if there's an outer giant planet or not, some people say this is needed to have a habitable planet. And then there are also 3 additional criteria. Of course, you need a certain amount of water, you need nutrients, and you have to be in the right galactic environment. So actually, this first definition, just the planet in a habitable zone, there are just 2 requirements, whereas I would call it the real definition, there are 10 requirements. Now, if the last 3 ones are not fulfilled, you do get life forms, but unfortunately only very simple ones. So that is basically the outline. So I cover only these 3 points, 3, 4, and 5 in this talk. Okay, let's look at the properties of exoplanets. That's the usual plot. And you see when you plot the mass of the planet against its density, then when you start with the brown dwarfs and the giant planets like Jupiter, they basically follow one track. The density, the smaller the mass of the object, the lower the density, because the size of these objects is basically the same. But then when we come to the low mass planets, there's a huge diversity, and planets of the same mass can either have a very high density or a very low density. And that is, of course, very strange. I mean, low mass planets are, in this case, the exception in astronomy. I mean, with stars, giant planets, everything, there's always a relation between, say, mass and density, but not with the low mass planets. What's the reason for that? The reason is, of course, the low mass planets have hydrogen atmosphere, and the higher mass, or the ones with the higher densities, they don't have a hydrogen atmosphere. And there are 3 possible explanations, and possibly all 3 mechanisms are involved. There's, first of all, this gas-poor formation scenario. So basically, some planets don't have a hydrogen atmosphere because they never get it. And the second explanation is they get it, but they lose it because of the internal heat source, which is coming from the formation of the planet. So basically the hydrogen atmosphere evaporates, making a rocky planet. And the last point is basically the X-ray and extreme UV radiation from the host star removes the hydrogen atmosphere. And additionally, you have coronal mass ejection that also blows off the atmosphere. And this is basically the subject of this talk, that we have this third process, so the removal of the outer atmosphere due to the X-rays and UV radiation from the host star. Okay, this atmospheric erosion, that is, of course, a very important process, but that doesn't mean the other 2 processes are not ongoing. Perhaps all 3 are ongoing. And that depends, of course, on the amount of X-ray and UV radiation from the host star. Now, my neighbor here in Potsdam, Katja Pockenheber, always points out that what matters is the extreme UV radiation, but the extreme UV radiation of M stars and also G-type stars is not a continuum, but they're emission lines, and it depends totally on the strength of these emission lines, which are basically coming from the lower part of the corona, or say the cooler part of the corona. And a star which doesn't have these lines, there the erosion of planetary atmospheres is much lower. Okay, let's start with the subjects, the cool planets of the cool stars. So planets of the M stars. First of all, the Sun is a G-type star. Why are we looking for planets of M stars at all? There are two reasons. First of all, and that's actually the main reason, is it is simply easier to detect low-mass planets of M stars. And transits are deeper, the radial velocity signal is larger, and that's just easier. And we have to think that 80% of the stars in the solar neighborhood are M stars. And then everybody says, oh, let's look for M stars, and we have the habitable planets very soon. And you have seen many announcements, the first habitable planet. But we have to keep in mind that the planets of the M stars are presumably very different from the planets in our solar system. First of all, the so-called habitable zone is much closer to the host star, which means all the planets have short orbital periods. That helps in detecting them, but on the other hand, they are so close that they are tidally locked. So one part, half of the planet is always facing the star, and the other is in internal darkness. That is, of course, one issue, that one side of the planet never receives any light, but the more worrying thing is that if a planet has a tidally locked rotation, then it rotates also slower, and most people say such a planet will have either no magnetic field or a very weak field. And the other problem, if the planet is close to the star, then the magnetosphere is also very small. So these planets have a problem with the magnetosphere, so charged particles can relatively easily enter the atmospheres of these planets. Then, of course, M stars are known to be quite active, and they emit a lot of flares. That's the subject of this talk, and that could be a problem. And this flare activity and the extreme UV radiation, that leads to the erosion of planetary atmosphere. That changes completely the photochemistry. So that removes this first assumption. If you put a planet like the Earth next to an M star in the habitable zone, the atmosphere will, after a short moment, not be like Earth because of the photochemical reaction due to the X-ray and UV radiation. And then, of course, it could be that the ultraviolet completely makes the planet inhabitable if it's very strong. And then what other people pointed out, because of the strong XUV radiation, such planets have enormous water loss, and so perhaps they are dry, and for that reason it's impossible that they have any life. So there are lots of problems with the potential habitability of the M star planets. But let's ask the first question, and that is, the whole thing, planets of M stars, is ridiculous if they don't have any planets. So let's first go to the first point and ask, do the M stars have low mass planets, yes or no? If they don't, then we are done. Okay, that is the project of the CARMNES consortium. CARMNES is a very big consortium of 11 institutes in Germany and Spain, and we all get together and build two spectrographs, red spectrograph and the optical, and an infrared spectrograph, to discover planets of M stars. And the reason to go to the very red part of the optical spectrum and the infrared is M stars are bright in that wavelength region, and simply the instrument is more sensitive if it gets if we use a longer wavelength. So what is the background? That's of course the classical plot that everybody always shows. That is on the x-axis, the orbital distance, and on the y-axis is the mass of the host star. When we have a typical M star, and this gray shaded region is the so-called habitable zone. The big dots on the top are, of course, the Earth in the middle, and then there's Venus and Mars. So you see Mars is also habitable, Venus perhaps not. And then you see these lines are the radial velocity accuracy that you need. And if you see, say, the M stars, M0, or even going out to M3, then you see we can detect with an accuracy of 1 meter a second, which is what we were aiming for with the spectrograph, a planet with the mass of the Earth in the habitable zone. Or a planet with, say, 5 to 10 Earth masses in the habitable zone, if we get an accuracy, say, between 1 meter and 3 meters a second. So we can detect rocky planets if we get, say, an accuracy of 1 to 3 meters a second, which CARMNES achieves. So CARMNES gets 1 meter a second. And our main sample was really the M3 stars. Now, with M stars, there's one very funny thing. You see that a massive M star has about 0.6 solar masses, and an M3 star only 0.3. So there is a factor of 2 in mass for the host stars. So an M star is not an early M star has a much higher mass than a late M star. So the M spectral class is defined a little strange. Okay, that's the telescope, the 3.5 meter telescope on Calle Alto. And in the lower left, you see one of the spectrographs being lowered into the Coudet laboratory on the installation. That was the most critical moment when our precious instrument was hanging here in midair. And then the first thing what we did was observing planets that were already known, and we confirmed most of them, but also some other ones. We found out that there is actually no planet. That was false positive, and we could clearly show that this radial velocity signal was activity, not a planet. Meantime, we have found a lot of planets. Now, this is a result from Silvia Zabotta's thesis, and she is almost finishing. And the other ones are studying individual objects, and our CARMNES team and Silvia produced this very nice plot on the table. So in the table, you see basically the mass of a planet in Earth masses. So let's look at this part, 1 to 10 Earth masses. And you see that the black here, that is the CARMNES value, 26% of the stars have a planet in that mass range, which is close in, and the fraction, well, could could be even larger with larger radii. The other interesting bit is the blue one is the old HARPS data that we did with CARMNES also detect a few giant planets at a large orbital radius, which the others did not. So that's interesting. So obviously we can conclude there are a lot of planets in the around M stars. So M stars are planets. In the plot, by the way, you see very nicely the mass of the planets versus the period. All these stars are the detected planets, and all these little gray symbols, that is the expectation from simulations. So we can conclude M stars have a lot of planets, but are they really habitable? And there are several factors that affect this. And the first factor is, of course, the XUV radiation. And what has been studied is the XUV radiation from the quiescent state, and also the quiescent stellar wind. And the conclusion was, while many planets of M stars can be habitable, but what has so far not been really studied in a lot of detail are the flares. And the flares emit a lot of 20 to 50% of the X-rays and UV radiation already in quiescent are small flares. So the flares make a big contribution to the total brightness at short wavelengths of M stars. And then there are the coronal mass ejections. So basically we have to study the flares, and the coronal mass ejection in order to find out if the planet is habitable. If the activity of the star is so large, then of course this affects enormously the atmosphere, and it leads to a lot of heating of the ionosphere of the planet. And perhaps because if the flare activity of the M stars is so extreme, maybe it's not possible that a planet in the habitable zone is really habitable. Okay, Priscilla, in her PhD thesis, she studied two stars, that is AD Leo and EV Lux. Both have an age of like 300 million years, because we want to study the activity of M stars at a young age. So basically when planets have formed, so the first part of their evolution. And for her thesis, she used data obtained with our 2-meter telescope in Tautenburg, which has an ejections spectrograph with a resolution of 35,000. And basically AD Leo and EV Lux is the same kind of stars. They are very similar. And the difference is AD Leo is viewed from the pole, and EV Lux is viewed from the equator. And both of them we observed for several hundred years, not years, but hours. And the reason is we wanted to look also for coronal mass ejections. And if we view one object from the pole and the coronal mass ejections go out via the pole, then we would detect them in AD Leo, and if they come out in the equator, then we will see them only in EV Lux. Okay, the flares have energy distribution which can be described as a power law. So mu is basically the frequency of flares, and E is the energy released. And the upper equation, so the log nu equal to beta log E, is the cumulative frequency. So basically you ask how many flares have an energy that have an energy higher than, say, 10 to the 30 ergs, do this star have? And this is a power law, so basically there are, of course, many small flares for each large flare. Then the equivalent is also, you can also describe it linearly, how many flares are in each energy band. And there are two exponents, so the beta basically describes if the energy comes out mostly in small events, or if the beta comes out mostly in large events. So if beta is smaller than -1, then most of the energy comes out in the small events, and if it's larger than that, most of the energy comes out in the small events. So that's what I will show in a second. This is basically a light curve obtained in the H-alpha line of a flare, which you see with the blue symbols, where you see basically a rapid increase and then an exponential decay. And also in the red, red is H-alpha and blue is H-beta, where you see in both cases a rapid increase and a slow decay. And in total, we found in the 200 hours of observation, 22 flares with energies 10 to the 31 to 10 to the 32 ergs. But the most important thing is that this beta exponent is, say, roughly of the order of 1. So basically the same amount of energy comes out in small and large events. But of course, in order to study the erosion of planetary atmospheres, we also need to know if there are coronal mass ejections. And these 22 events were all very large. To give you an example, the largest flare observed on the Sun has 10 to the 30 ergs in the whole continuum. And so they have 10 times the energy just in basically one line. So these are enormous events, so you should expect to see coronal mass ejection, but we saw absolutely nothing. And of course, 22. And we expected that we should see at least 10 coronal mass ejections in the flares that we have observed. And using the relation between the amount of mass ejected in a flare in a coronal mass ejection on the sun in a flare of a given energy, we can calculate how much mass is ejected. And we can see if we see that in the spectrum, and we didn't see anything. And here's basically a little simulation, depending on the speed of the coronal mass ejection, how the profile would look like. So the black line is the observed profile, and say the blue line is how the coronal mass ejection should look like with the expected mass. And of course, you can say, okay, we didn't see anything because the velocities of these events is very high. But of course, when you see many events, then it's very unlikely that you view them always coming directly towards you. And so that is a little bit unlikely, but we made the second test. We studied also EV-LAC, which is basically the same star, but viewed equator on, and we observed it also for 130 hours. And we also saw many, many flares. And we saw also the continuum increase, and what is really amazing, we also saw the helium-2 line. And helium-2 is very interesting because it comes from a relatively hot plasma. And also you remember that the UV radiation there also comes out on several lines, and one of these is a helium-2 line, so it's very nice that we see this line also in the optical. And then we derive the beta value again. This is now a little bit smaller, or it is significantly smaller than in AD Leo, but I wouldn't worry too much about it. And apart from the spectroscopic data, also the TESS satellite observed the object. We also saw lots of flares. And also the beta value is again consistent with our observation in spectral lines. So again, lots and lots and lots and lots of flares. So what about the coronal mass ejections? I mean, we take out now the geometry, and the answer is we saw absolutely nothing. We saw no component with an escape velocity of 600 kilometers per second. But we did see one event where the blue asymmetry was 200 kilometers a second. And this is lower than the escape velocity. So presumably, this was more like an erupting filament. And this was not related to at least a big flare. I mean, there was a little bit of an enhancement, but there was not related to a flare. And so again, no coronal mass ejections. So what we found is then that basically lots and lots and lots and lots of flares, but no coronal mass ejection. And as I will explain later, this is pretty typical for M stars. Then we made another study. Now this is the thesis of David Wockel, where we observed a cluster of stars which are even younger, so between 5 and 10 million years old, which is basically the main erosion phase of the planetary atmospheres. So planets have just formed, and now they're exposed to the XUV radiation. And the question is, how much is it, and are the atmospheres completely eroded, or do they survive this say, horrible radiation? And luckily, this Upper Scorpius region was observed with the K2 mission, with the Kepler satellite. And we have a very long photometric monitoring, so lots and lots and lots of flares. But there's one little problem that, of course, many years ago, we identified the Upper Scorpius stars using low-resolution spectroscopy. And while with M stars, they have lots of lines, so we were not absolutely certain that all the identifications are correct. So we also took with the VLT and flame spectra to confirm that these stars are really members. Some of them turned out not to be, but now we have a list. And then thanks to Priyanka, we also started the monitoring using the Mount Abu telescope in India. Upper Scorpius is too far south for Central Europe to be observed, so one has to go to India to do this. So just to show you a light curve, you see very nicely the variations due to of the continuum, and on top of it you see the flare events. You see very nicely there are really big events. It's very easy to find flares in them, and also the little events here, they are all flares. So we found one super active star, which has this wonderful telephone number. We confirmed that it's an Upper Scorpius member from the lithium line, and also has, of course, a strong H alpha line, which is typical for active stars. And then we derived the mass. And here's something interesting, because these stars are so young, they are still contracting until they reach the main sequence. And this one has 0.6 solar masses, which means it's a K star once it is fully on the main sequence. It's also, you see, it's still larger than the sun. And it's roughly 1,000 times brighter in X-rays than the sun, so really active. Why did we select the Upper Scorpius region? Upper Scorpius is very interesting because the very same data that we used for the flare study was used to discover a planet, and this object is named K2 for the K2 mission, number 33. And this planet is basically an object which is a little bit larger than Neptune, but it's a Neptune-like planet. So it's one of these objects that if the erosion rate were really large, this one would convert to a rocky planet. So when we find rocky planets among the old stars, it could be that the progenitors is such an object. Now, unfortunately, we don't know the mass of this planet, but what we can do now is measuring the flare rate and calculating how much energy is put into the atmosphere, asking the question whether the hydrogen atmosphere of this Neptune is completely blown away by the stellar activity to form a rocky so-called super-Earth planet. And if the mass of this planet is, say, below 10 Earth masses, the atmosphere would be completely removed. So that's a possible project. What we also did, I mean, we studied the flare frequency of all stars in Upper Scorpius, and here is the plot for the M stars. So you see the power law. Mu is the frequency of flares per hour, and so every 10 to the 4 hours, you get one flare with 10 to the 35 ergs. Remember that the largest solar flares are below this plot somewhere here. So the 800 flares that we did observe were all larger than the largest events on the sun. But what is interesting is this power law is larger than -1. And that is the case for the most active star and also for the average M star at this age. So the results of, say, our flare study is that young stars are super active, and flares contribute very significantly to the XUV radiation of M stars, and the younger the star, the larger the contribution. Then we found this beta value, and since beta is 0.5, it means that it is the case that most of the energy comes out in the large events rather than the small events, at least for the very small ones. Now, there is also a recent work from last year where somebody studied all the M stars in the TESS that TESS has observed and also derived the flare rate. Now, unfortunately, they only put a plot in the paper, but didn't derive it. So with a pencil, I had to do it myself. And they studied basically also young M stars and found basically also that this beta value is larger than -1. So most of the energy comes out in the large events. Then we studied it in AD Leo, slightly different. And but otherwise, the main thing of the AD Leo study is that there are no coronal mass ejections. Now, there's one work which is also interesting that is in the book from from Helmut Lammer, and there's an article from Linsky in it, and he's cited several papers where they studied the Lyman alpha absorption, the interstellar, and this absorption comes from all the mass that stars have lost. And there is a nice relation. The more active a star is, the larger is its mass loss. That is with the normal wind and also the mass loss due to coronal mass ejection. But then there's a dividing line, and if a star is super active, then the mass loss is suddenly lower. And you see here's also EV Luck. And if you calculate it, then the mass loss of EV Luck is about the same as the sun. So the mass loss due to wind and including the coronal mass ejection is for a very active M star not that extreme. So it's not surprising that we didn't see any coronal mass ejection. They are not, basically, there are only very few of them. There is mass loss, but it's not so extreme. Okay. And then one thing I would also like to point out is the composition of these planets. I mean, when you look in the literature, then everybody says a rocky planet has to have the composition of the Earth. Unfortunately, this is more future project because the density measurements of planets still has relatively large errors. But I would like to convince you that this assumption is actually presumably invalid. Why is the internal structure of a planet so important? The reason is that if the composition of the planet is very different from Earth, it is very likely that it cannot produce a magnetic field, and the magnetic field is needed to shield the planet from high energetic particles. The other thing is also we need the so-called plate tectonics in order to remove the carbon dioxide from an atmosphere into the ground, and in this way the planet becomes habitable. And if the internal composition is wrong, then this is also goes in the wrong direction. So if the composition of the planets is really very different from Earth, it's very likely that they are not habitable. When you want to study it, you better select planets where you know that there's no atmosphere. Otherwise, you have three free parameters and only two quantities. So you go for the ultra short period planets, which at least don't have any hydrogen atmosphere. They are too close. Then there's one interesting work which I would like to show you. Of course, the composition of a planet can be changed by impacts. So if there's an impact, then the outer parts of the planet is removed, and usually it gets more iron rich because the outer silicate part is moved away. And here's a paper by Scora, and what they did was they plotted the density measurements of from the literature against a model where they included all these planet-planet interaction and the impacts, and found that this distribution cannot be reproduced with just with impacts. The spread in density is too large. Then one paper I want to cite and then come back to our own work is that Caroline Dawn pointed out one of the reasons why there is such a big spread in composition of the planet is that the temperature in which certain elements condense is very different. So the highest condensation temperature is aluminium. So a planet that forms very close to the star will be aluminium rich. And it cannot be, say, silicate rich because silicate doesn't condense out. So the condensation temperature determines the chemical composition of planets. And depending where it forms, it can be very different. Now, she pointed out that the highest condensation temperature is aluminium. So let's look at the density. And most of these ultra-short period planets have surprisingly low density, and it can be shown that this is not the atmosphere. It's really the composition of the planet, which means that most of the inner planets really form close to the star, and they are aluminium rich. So 66% of the planets have a composition which is inconsistent with the Earth. So the majority, the Earth is strange. So we contributed also to that plot one very interesting planet, which is a planet which is in the other direction. It's not aluminium rich. It is. It has an extremely high density of 13 grams per cubic centimeter, and it's very iron rich. we are not the only one finding such planets, and actually there are a few of them now. And the most likely explanation is this is not formation, but it's a collision. So, conclusion, it's actually very unlikely that all the rocky planets have the composition of the Earth. Why is that? First of all, the condensation temperature measures, basically where the planets form. And the second is impacts change, and we know that there's a lot of impacts. And also we have to think that the composition of the Earth is unusual because of the impact which formed the moon. And then, of course, the host stars have various abundances. They are not all solar-like. And in fact, 60% of them could have an Earth-like planet, at least magnesium silicium, but 40% not. And when you go to the carbon to oxygen ratio, it's actually very rare that you find a star which has a composition like the sun. So that's the reason why it's very likely that the composition of exoplanets is very diverse. We have the effect of the condensation temperature, we have the impacts, and the host stars are also different. So why should they all be like the Earth? Now, in the last 10 minutes, I will go a little bit in the future. What are the next steps? So what we have hopefully convinced you is that M stars have a lot of planets, but they are very unlikely to the planets of our solar system. First of all, the star is very active, stays active for a long time, and this changes the atmosphere significantly. And then in the second part, I try to convince you that if we get very accurate measurements, presumably the result will be they will not all have the same composition as the Earth, because the stars have different compositions and because the other effects during the formation. So for that reason, my conclusion is that really Earth twins should be rare, particularly rare around M stars. Next step are 2 satellite missions. One is going to be launched in 2026, the other 2028. And 2026 is the launch of the PLATO mission. PLATO is an array of little telescopes, and the study shows that many small telescopes are much better if you want to find transiting exoplanets than one big one. And so PLATO has 24 little telescopes and then 2 so-called fast cameras, which are only 12 centimeter aperture, but they each of these cameras, or the whole field of view of PLATO is 2,000 square degrees, and the aim is to look for planets which have the size of the Earth, orbiting actually G-type stars, but orbiting G-type stars that are very bright, that can be studied in detail. So the main PLATO targets will be stars of, say, 9th, 10th, 11th magnitude, and these 2 so-called fast cameras are for very, very bright stars. Then the other mission is Ariel, and Ariel is a mission to study the chemical composition of planetary atmospheres. Of course, you have heard that Ariel can do maybe the atmospheres of a few super Earth, but most of the targets will be actually Jupiters and Neptunes. So why do we want another exoplanet search mission? And the reason is that we are going for bright stars, but in contrast to TESS, which is flying now, also bright stars which have a planet in the habitable zone. So for that reason, we need a long monitoring time and a big field of view. And TESS looks at a field only for 20 days, so basically for short period planets, except for the poles. And so PLATO will be 10 times better than Kepler to detect planets in, say, between 100 days and 500 days periods, and 1,000 times better than TESS, because TESS can do this only on the poles. But the improvement over Kepler is actually very large, because Kepler had the problem, it discovered thousands of planets, but only about 100 of them we could characterize well, which means measuring the masses of the planets. And all the other ones are basically, you just know that there's a planet, and that should be different with the PLATO mission. And that's why we want it. And then everybody says, oh, if you want to measure the density, you need the diameter, which you get from the light curves, and you need the radial velocity measurements, and you do this always espresso. And when we go back to this one number, that there will be 4,000 super Earth, and at least 40 to 70 in the habitable zone. How much observing time do you need? And the answer is at least 199 on espresso. Espresso is on the VLT, can be operated with one, with two, or with four of the UTs. And 199 on the VLT is impossible. And also one has to think, if one wants to detect or measure the mass of an Earth-like planet in the habitable zone, even if your instrument can do it, most of the stars will be too active to detect the signals, actually 80%. That means you spend 190 nights on the VLT, and 80% of that time is wasted because you don't have, you cannot determine the mass because the star is too active. And that was the first starting idea of the PLATOspec project, which is a collaboration between Tautenburg, the Universidad Católica in Chile, and also with the Andreev Observatory, and very recently also the University of Brno joined. And the aim is, or the first aim of PLATOspec is to observe all these 4,000 planets or host stars with hosting planets that Plato will discover, and measure the stellar activity. And here's a plot of the activity of stars in the solar neighborhood. And you see these are the famous calcium lines. On the left side are the active stars, and on the right side, the very inactive stars. And if you estimate you want to discover a planet which has only, say, 1 or 2 Earth masses, what kind of stars do you need in order to be able to detect this planet with, say, 100 spectra or so? Then you find out that depending on the mass of this planet, if it's 1 or 2 Earth masses, either you have only a third of the stars are inactive enough that you can do it, or it's even below 10%. So you have to observe 9 stars and only 1 is inactive enough that you can discover an Earth-like planet. And that is the reason why we want to measure the calcium lines of all the objects that Plato will discover. Yes, and of course, the other reason is that the calcium lines are also very good indicators for the activity level of the star in general. So they can also be used in order to estimate what is the XUV radiation from the stars. And in this way, we can also say, okay, this star has a certain activity level, and if there's a planet in the habitable zone, that will be the erosion rate. Okay, then, of course, I pointed out that there's Ariel, and Ariel will, of course, observe a few low-mass planets like Earth and super-Earth planets, but most of the object will be actually Neptune and Jupiter-like. And Plato will actually discover many of these. And so the second science goal of PLATOspec is to measure all the masses of the Jupiters, which basically nobody else is interested, because they say, oh, who's interested in a hot or a warm Jupiter? And we are interested in them because these are the prime targets for the Ariel mission. And here's a plot from the proposal. So depending on the temperature so, they are very interesting because they have many, many different cloud layers. For example, the L dwarfs here, they have 1,000 or 2,000 Kelvin. They have 3 cloud layers, and of course, for the Ariel mission, you want to discover these, say, warm Jupiters, and you want to provide Ariel with the warm Jupiters. Even more exciting is, of course, when you discover cooler planets, and these are then the input objects for the Ariel mission. So what is PLATOspec? PLATOspec is will be mounted on the old ESO 1.5 meter telescope at La Silla. It's a fiber-fed Echelle spectrograph with a resolution 70,000. So pretty typical for these high-resolution spectrograph to do precise radial velocity measurements. And then the accuracy that we want to achieve is either 5 meters or 3 meters a second with 2 different modes. The say less accurate mode is the one where we use the thorium-argon simultaneously calibration, and the 3 meters a second we go with the iodine cell. Of course, we try to build the spectrograph as precise as possible, but we don't have enough funds to make it a vacuum spectrograph, so it will not be evacuated because this will triple the price. And from the CARMNES project, we know how expensive a spectrograph is, which is temperature stabilized and evacuated, and we don't have these funds. So that is why we go with one which has air inside. But nevertheless, if we reach between 3 and 5 meters a second, which is our prime goal, then that would be sufficient with 100 radial velocity measurements to discover a planet with 0.2 or 0.3 Jupiter masses in a 6-year orbit. And basically what we can study is for Ariel all the hot and the warm Jupiters, but also actually the cool Jupiters. And for the PLATO mission, we can do the stellar activity, and we can also look for outer gas giants in systems where there are inner planets which have a few Earth masses. And that needs a slightly longer monitoring time of a few years, but it doesn't need a very, very accurate spectrograph. What we need is a lot of observing time. And the observation will be done first remotely and eventually robotically in the second step. So the calcium lines, I would like to show them. Of course, we are going for relatively inactive stars, so it's actually not the lines, but the core of the lines we are interested, which are tracers for stellar activity. And we estimate that we get a signal-to noise of like 40, which would be sufficient of even the faintest objects that PLATO will really provide us. So all the PLATO objects which are really interesting, we should be able to do. Okay, this is the schedule, and you see that the whole project started in 2019, and the big event was December 2020, so very recently, yeah? Very recently, that we got the funds to build it, and 2023 we go to the instrument, and then we can really observe with PLATOspec. And you see that already at the end of this year, we will have the telescope being refurbished. In the meantime, we use the Pucheros Echelle spectrograph from the University of Católica. So beginning from next year, we can actually observe with the telescope and a spectrograph, and only then in 3 years we get the full instrument. Okay, let's come to the summary. M-Star have a lot of planets, but we cannot just say, oh, they are all Earth-like because they have the right distance from the star. They are quite different. They have synchronized rotation. One side is always facing the star. Presumably, they don't have a magnetic field. M-stars are super active. They have a lot of flares. And they stay in this active, high activity mode for a long time, and that changes the whole photochemistry. It leads to erosion of planetary atmospheres. It leads to the water loss. So all these things make it very likely that at least the atmospheres of these planets will be really different from the Earth. Then also, I think We don't have really good data yet, but I think there's growing evidence that the composition is not Earth-like. Why? Because we are certain that the impacts play a role in the evolution of planets and their formation. We know that the condensation temperature play a role, even if all the disks are the same. And we, of course, know that the stars are all different, and stars and planets basically form from the same raw material. So if the stars have different composition from the Earth, why should all the planets be Earth-like? The other thing which we will address in the future with PLATOspec is does the structure of the system matter in terms of habitability? And we can imagine 3 different structures. That is a star with just one rocky planet around it, or all these compact systems which have been discovered in, for example, by Kepler and also the COROT mission, which flew before. Or do we have also many of these systems like our solar system, where we have a few rocky inner planets and then giant planets outside? And so it's not at all boring to look for the outer giant planets. And that is one of the aims of the PLATOspec project. Of course, the activity and the age of the star matters when you think of habitability. We will also address that point. And of course, we want to study the composition of the atmospheres of the planets with the Ariel mission. And of course, this can only be done with Jupiter's, but it gives us a first glimpse of how large the variety of planets is. And then I come to my conclusion. It is, I fully agree with this article that life can exist, perhaps on many planets, but this evolved life that we have on Earth, that requires presumably very special conditions. And we should be very careful when we book a flight to a planet which is supposed to be habitable. And when we go there, it turns out that it's not habitable. So be very careful when you go to the travel agency Interstellar and you start booking flights. And then my last transparency, and that is, you have seen that I presented, I mean, part of my work, but a lot of work and most of the work actually done by my students, and I want to thank them. But my conclusion is my students do very nice work, even if I sit in the cafe house, and I would like to thank you for your attention.
Thank you. Thank you, Eike, for a very interesting, very nice talk. And I hope that we can continue the discussion in the cafe house here in Graz very soon.
Yes.
But before...
And you see also which cafe house this is.
I know I do not recognize that.
Hilmteich.
Hilmteich, exactly.
Right. I'm also there frequently.
Okay. I'm not yet long enough in Graz. You need to take me there. I'm Viennese. So, but before we can meet in a cafe house, there are 2 things. First, Corona needs to be
yes.
bet, and we now have the chance for a discussion session. So, who would like to start the discussion? Please simply speak up. Yeah, Manu, I see your hand raised.
Thanks, Eike, for the very interesting talk. Maybe I missed it, but I guess you didn't mention. You said there is a break in the mass loss for M-class stars. What about the stellar wind speed? Are there any estimates for that as well? I mean, is the low mass loss due to the low density of the corona in the M-class star, or is it really? I mean, is it a specific thing due to the low speed of stellar wind?
It's a little bit of a speculation, but there is, I think, growing evidence that topology of the magnetic field matters a lot. And if there's a, say, relatively strong magnetic field overlying the flare region, then you get a flare and you get mass ejected, but the mass, the ejected material flows back to the star. It's a little bit of a speculation, but I think that is very likely. And what I've seen is you don't need a very big field overlying this region. And my guess, it is the topology of the field which basically prevents the material from really escaping the star.
Right, but are there estimates on the stellar wind speed itself without coronal-mass ejections?
There are also estimates, and I have to think about it, what the estimate is. But as far as I know, that wasn't such a critical point. I think the speeds are high enough that the matter could leave the star. But and in principle, if the topology is right, but so the speeds are higher than the escape velocity. But the problem is the topology. That was my understanding.
I mean, I was specifically asking because of the compression that makes us seem nicely visible, especially in white light, is also related to the ambient speed,
Yes.
the flow speed. And if you have a fast stellar wind, ambient stellar wind, then you might not really recognize it from the overall or general outflow of the star. That was my point here.
And Petra Oder wrote a paper with going through all the arguments why we don't see coronal mass ejections. And there are, of course, several possible explanations. And one thing is, of course, observationally, I've shown this. If the speed is really 6,000 kilometers a second, we wouldn't see them in the spectrum. And the other reason argument was, if the speed is very high, then the material flows out so quickly that we miss this moment, and also the dilution is so fast that we would see it on the sun, also if we really have imaging, but in the spectrum we wouldn't see it simply because there's not enough photons coming out of this material within the, say, 15 minutes of integration time. So, of course, that is uncomfortable if it's an observational bias, and that is why I showed, where was it? Conclusion somewhere here. Just had yes. Why I showed this, because that is for me the only evidence that the mass loss is currently really low, because what they measure is basically the absorption of all the material leaving the star in Lyman alpha. And because the absorption is low, that's for me an indication we are not missing these events. It's really they are not there.
Okay, thank you.
Well, small, yeah.
May I add on? May I add on here? Thank you. So first, thank you very much for this really very, very interesting talk. I also somewhat think that it might be that the events are not there, really due to the strong magnetic field, and particularly if you look at the most active stars somehow, which probably have the strongest fields. And there's also a recent paper by Lia in 2020 on the Sun. But that was nicely shown if you just plot the flares, the big flares, as a function of the magnetic flux of the active region. So the most simple thing, how strong is the field? You come to a certain threshold, which was roughly that 10 to the 23 Maxwells or so, where you have all the flares, but suddenly most of them are confined and have no CME. So still, and I really think when I found this, I was quite surprised that it shows up so nicely, because there seems to be a threshold which then also can produce a break in all of these kind of also mass flows. If you have a certain range where like the CMEs cannot escape anymore, so the mass is really confined by a strong overlying magnetic field, which I would expect scales with the activity of the star also. Very interesting.
That's exactly also what I thought. It's this relatively strong overlying field.
May I add a question? Another one. You said that in one event you found indications for a prominence eruption, but you say it's no CME. How do you distinguish, or why do you call this a prominence?
We were very surprised because we thought that the referee would say remove this, and the referee said no, this is fine. it's a very indirect argument. First of all, the velocity speed is not very high. It's only 220 kilometers. Then, of course, there's the geometry effect that one can say, okay, this was a CME, which is not going directly towards us, but it was not connected with well, I would almost say any flare. There was, when you look very carefully, you could see, okay, there was a little event. And also this little event was somehow strange because it was not like a classical flare with a rapid increase and exponential decay. It was a little increase of the brightness over a longer time. And then it went back to normal. So we thought, maybe we write this with the erupting filament, and the referee will say no. And the referee said, okay, that interpretation is a possible interpretation. Of course, I wouldn't be absolutely sure, but from the fact the speed is low and not associated with any, say, normal flare, we had this interpretation. But of course, with the star, the problem is you don't have an image of what this is. And the other thing
is interesting. The prominence for me would be just the inner part of a CME, and this can also come from quite sun regions and without flare.
Yes, I should also mention what we saw actually was first the blue shift, and after there's a red shift. So one could imagine material flowing up and flowing down again.
Some point down. Okay.
Could be that it's an overinterpretation, and
I think it's fine. I would even not be so much concerned about the speed, because even, I mean, I would expect if I see a CME prominence eruption, you would see it rather close to the star when it's not so much diluted yet, and then it might be still in a phase where it's increasing its speed. Like, I mean, at the sun, there's many CMEs which are below the escape speed when you observe them, but of course they're not below escape speed, but they're still kind of driven, magnetically connected, and they still increase their speed. Then,
Yes, I also read this, that basically, I mean, we see them only in emission lines. And basically, once they reach the escape speed, the flux from the emission lines is so small that we don't see it. That's, of course, another argument. So there are actually plenty of arguments why there could be still coronal mass ejections, which we don't see.
Interesting. Thank you.
Yeah, thank you. I would like to encourage all the students and also our guests to raise questions. So please.
I think there are some questions in the.
Yeah, that's the next thing. But you can if you don't have a microphone, please type it in the chat. If you have a microphone and you would like to speak up, please raise your hand, and I will simply take one after the other. And the first question in the chat is from Marcel Ploy. Do you want to read it out, Marcel?
Yeah. Hello again, and thanks for the nice talk. I mean, the second question I had, you already discussed with Astrid, so I'll just ask the first one. I mean, it's clear that it's easier to detect low-mass planets around M stars, but due to the fact that M stars themselves are harder to detect because of the lower luminosity, were there actually more low-mass planets detected on M-type stars than on other type of stars in general, or do you detect more low-mass stars on other types of stars?
The problem is just the sensitivity. I mean, a G-type solar-like star emits all the light basically in the visual wavelength spans, and until recently all the spectrographs were in that wavelength spans, and they were wonderful. And the problem with the M stars, they are very faint in the optical, but most of the light comes out in the near infrared. Now the density of lines also decreases in the infrared, and so there's a sweet spot. If you have a spectrograph that works between, say, 800 nanometers and 1200, that's the best instrument. And up to now, and CARMNES was the first one that works in this wavelength region. And after we built that one, it was relatively easy, and now there are 3 or 4 such spectrographs. So that is why the number of M-star planets is increasing. Also, the TESS mission is optimized to look for planets of M-stars because, of course, they also wanted the habitable planets, and they knew that they would stay only for like 20 days or so at a field. And that is why the number of M-stars planets is going up steeply. And I'm just trying to find the statistics. The number of planets, so the statistics is that M stars have more low mass planets than G-type stars. So in fact, they have a lot of low mass planets and even more than the G-type stars. So a lot of planets are present around M stars. Let me see. Yes, here's the statistics. I do this again. Oh, I hope you can see it. And 20, so basically 26% have a planet with 10 Earth, between 1 and 10 Earth masses, with a period between 1 and 10 days. And when you go out to 100 days, it's even 40. So if you add up these two numbers, then there is 62% of the M stars have a close and rocky planet. That's a huge number. It's higher than the G-type stars, though they have a lot of planets. What is missing with the M-star planets are the Jupiters. And we were surprised that actually with CARMNES we detected a few.
Okay. In the meantime, there's a question from Martin Leitzinger.
Oh, I hope I can answer this.
He doesn't have a microphone, so he put it in the chat. For how long did you see the prominent signature? Was there an evolution visible?
Yes, there was definitely an evolution. We first saw a blue shifted component for, I think, like approximately half an hour or maybe a little bit longer. And then we saw the red shifted for several hours. Now, out of the blue, I would say for half an hour, we saw the blue shift, and then for 2 hours, the red shift. So actually, there was an evolution. And 8 hours is a night, so we were very lucky to cover the whole events. And I think the whole thing lasted 2.5, 3 hours or something.
And Martin continues with, moreover, do you think that we are done with the method of Doppler shift emission absorption as it requires high signal to noise observations, which are hard to get? What else to use?
What else to use? I mean, one thing that people always argue is radio astronomy, and because there you would also see the coronal-mass ejection. But my understanding is the sensitivity of optical observations is still so much better. And basically, if you put in CME from the sun, and you would ask, would I see this on, say, a nearby G-type stars and the optical? And the answer would be more likely yes, rather than in the radio regime. And I think the problem with the radio is the lack of sensitivity and the long monitoring time. I'm not sure that we are done already with this method. I think we should try to continue it because, I mean, up to now we studied a few examples. And maybe these are also oddballs. I mean, one thing, I mean, with the PLATOspec, our 4 institutes then have 80% of the observing time in Silla, and this is no longer here snow, rain, and in Tautenburg. So I think I would do it also from there because of the higher sensitivity, and then you get, say, for a week every night 8 hours or something. And I think once we have PLATOspec, that would be actually the first thing to do it spectroscopically because of the the problem with the Tautenburg data, I mean, it's wonderful, but well, maybe Graz weather is not so different. But you rarely have full, complete nights for several nights in a row. You observe like 3 hours in one night, and the next night another 3 hours, and you see the rise of an event, but not the decay. And I think repeating this with a telescope in a good site, Tautenburg is wonderful, but at La Silla, I think that still would be a big improvement.
I think you should also do the 100 years of observations you mentioned.
Yes.
All by yourself?
Yes, yes.
Okay, next question comes from Desmond Grossman, and then there's also one from Arnold Hanselmeier. And please continue by submitting questions.
My question is actually concerned with this slide.
This one?
This one with the distribution. And you basically have here the distribution with very good, to say, very acceptable error bars and uncertainties. The only value that shines out is the one for 1 to 10 Earth masses for 10 to 100 days, which is exceptionally high in uncertainty compared to all of the other values. And I was just wondering if there's a real explanation. Of course, this is a higher period, and this is more difficult to detect, but why is there so much higher uncertainty, which is basically sometimes even 10th?
And then I should explain a little bit more this plot on the left side and make it larger. Yes.
Yeah.
Little waiting. Okay. This plot shows the mass of the planet, and this color is the detection probability. So the yellow color means basically 100% detection probability. And you see that most planets are in this violet regime here between 20 and 40%. So the problem is that you say you take 100 spectra of a star and you find, say, one planet, and then at the same time, the detection probability is only 20%. So from the fact that you find one planet, then you know that there are 4 other ones which you haven't detected simply because of the number of measurements. And this is one of the proposed projects. Instead of observing other stars, just continue the stars that have been observed and take just more measurements. And Silvia made a detailed study. If you take 100 spectra of each object, then you would populate also this lower part of the diagram. Now, by the way, this is 3 years of observations on a reasonably good side, 80% of the telescope time. So it's already, I think, 20 or 30,000 spectra in this diagram. So it's not easy to make it much, much better.
I see. So I just wondered about exactly this value.
Yes. It's simply the number of spectra per star that go into it.
Yeah, I see.
One more remark. The nice thing is the Hubs and the CARMNES agree reasonably well.
Yeah, they do. Seems like. Agree quite well. Thank you very much.
Welcome.
Arnold, do you want to?
Yes, let me try to ask my question. First of all, thank you very much, Eike, for this very interesting talk, as usual. I have a non-scientific question, but you have shown us these ambitious plans, and I'm interested, how are these plans affected by this COVID situation we have at the moment?
This schedule.
This schedule, yes.
yes. The good thing is the main telescope. We are upgrading the whole, refurbishing the telescope this year. Now, The good thing is the company can do it in the Czech Republic and doesn't have to go to Chile. And they can build everything there. The only problem is that somebody has to go to La Silla and deinstall the motors from the old telescope and send it to the Czech Republic. And of course, one critical thing is that has to be done, say, until June. And we hope that until June that there is a little time. I mean, they just need a few days to go to La Silla, deinstall the motors. And then we hope that after the summer, the COVID situation is such that we can go to La Silla.
Yes, everybody hopes that.
I mean, if this is, and we are safe until June, and if we say up to now we can do everything here and just we need some parts, then we are still in the schedule.
Okay, that's great. Okay, so good luck.
Thank you. I mean, yes.
So, if nobody else has a question, I take the last question. Mm-hmm. You were talking about if all the planets are the same, and basically it depends on the temperature they are exposed to. But I also wonder, how does the mass uncertainty of the planet estimate propagate into the composition of the structure?
That is a very, very important thing. I mean, do you see this large enough? I can make it large.
Please do it large, yeah.
Okay, so you see basically the error bars. And one of the main thing of Plato is really making these error bars 10 times smaller, because only then we see an effect. When you look at these error bars, then you see, okay, in most cases they overlap, and you have to do very fancy statistics to see that this variation is not just due to measurement errors, but it's that there's a real scatter behind it. But at the moment, really, the problem is the accuracy of the measurement. It is on both sides. The diameter of the planet and the mass of the planet. Now, the diameter of the planet, the funny bit is that with Plato, actually, it's not the depth of the transit that matters, is the radius of the star. And there we actually hope for these guys doing stellar astroseismology to improve that. And astroseismology is absolutely important for that. And the mass is also, it is the mass of the star that contributes very significant to this error bar. And also in that case, it is basically the knowledge about the star is very important. Now with the radius, we have one big advantage. This is Gaia. And I now found out that with the Gaia measurements, for most of the Plato objects, you get the radius simply from Gaia together with infrared photometry already down to, say, percent level, which is a very, very big improvement over this. But the errors are, I mean, that's a little bit of you in the future to do all this fancy density stuff.
Okay, I'm glad to hear that our jobs are still secure.
Yes, absolutely. I mean, really, astroseismology is the one key advantage of Plato, that you can do astroseismology on the planet host stars. And that is essential for determining the stellar properties.
Yeah. Yes, it's a very important or very helpful independent source. You dropped the right password. I will pay you a beer in Graz when you're here.
Okay, thank you very much. Or the cafe.
Or cafe. Maria Pia.
Oh, yes, I was just
sorry
giving a comment on the astroseismology of M-stars. Unfortunately, it would be unlikely that it would be possible to do.
But Kepler did
I don't want to spoil it.
Now, one remark to that. One second. Just one little second. Yeah, I know here. You're absolutely right. When you read the papers and you calculate the amplitudes using this paper from Kelden, I think, then the amplitudes are so small that you cannot detect it. Now, together with Constanze Zwins, no, it was Constanze Zwins with many people, and then me at the very end. We submitted a paper on exactly this star, which is now accepted, in which the detection, actually the first detection of oscillation of an M star is claimed. And I was very surprised that it was accepted. So it's also this object. But don't ask me about oscillations. Ask Paul about oscillations. I'm not sure that these are the standard G modes which we know from the sun. As you say, the amplitude should be so small that we will not be able to detect them. And by the way, there's always this dream to detect the oscillation on Jupiter, and I think was never successful, even on Jupiter.
Not to my knowledge.
Well, from the theoretical point of view, we should be able to see. I mean, oscillations are excited, but unfortunately, due to the extreme activity of this kind of stars, it would be very difficult to detect. But yes. I'm looking forward actually to read your article and to see better news actually on this point.
Yes, PLATO, I should have said this more clearly. PLATO is for solar-like inactive G stars, so it's really old solar-like stars, so it's 5 minutes oscillations. And there we know that the amplitude should be roughly the same as on the sun. That's the science goal, so it's not the M stars.
Sure.
Well, if we learned one thing from Kepler and TESS is we know what we get when the satellite is flying. So let's simply cross fingers and look into a bright future. Okay, I would like to thank Eike again for a very interesting talk and a very lively discussion session. I would like to thank everybody who participated in the discussion session or as in the audience. And yeah, we will continue with the Astrophysical Colloquium in Graz, and I hand over to the other chair of the Colloquium, Manuela Temmer.
Thank you, Paul. So yeah, we will go into a bit of a break, a spring break, and we'll continue our colloquium on the 3rd of March. So if you're interested in a talk by Jörn Warnecke, he is from the Max Planck Institute, and he's working in the Solstar group on solar and stellar dynamo actions. I guess also quite a subject that is bridging solar and stellar physics, and I hope that many of you will be interested in that. So that will be the 3rd of March. Again at 5 p.m. and we will send out we will send it out to you, and hope that we hear and see us in March again. Thank you.
And thank you for inviting me for giving the talk.
Thank you for coming.
Sure.
We had to convince you. It was quite some work.
Oh.
And yeah, as you have seen, we announced this meeting via the Task server, and this year we will continue, so you will not miss our talks. And every 3 weeks we will have a seminar. Stay tuned. Manuela and I are working on a good lineup of talks and speakers. With that, we're astronomers. I wish you a pleasant evening and a long night, long photometric night.
Clear skies to everybody.
Clear skies. Carpe noctem.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.